Swayam Prabha. Digital India. Educated India.
Hello and welcome to this lecture of the course Elements of Mechanical Vibrations. In the previous sessions, we did discuss the modal analysis approach for multi-degree of freedom system, both undamped case as well as a damped vibratory system. However, in today's session we are going to focus on the orthogonality of eigenvectors through a simple example, so that you understand what it actually mean physically or geometrically, and that will help you to understand orthogonality in a better way. Okay, we have discussed the mathematical expression for the orthogonality of the mode shapes. In that we have shown that UR transpose, let us say M or K, the system matrices US, this is equal to 0 if R is not equal to S. That means we are talking of two different modes, and is not equal to 0, it is a non-zero value, some number if R is equal to S. Okay. So, this orthogonality of mode shape is mathematically very well defined, and we know that, but we did not really understand, or probably we have not discussed as to what do they physically mean actually. Okay. So, I am taking a small example here which may give you some idea about the orthogonality per se. Okay. So, let us take an example of a simple 2 degree of freedom system. Okay. This applies to multi degree of freedom system, but for the sake of simplicity and ease of demonstration, I am taking this system which is point mass, which is held by 3 springs. As you can see, the blue colored ones are the springs K1, in springs S1, S2, S3, and each of them are having different values of the stiffnesses along their axis. Okay. So, it is a point mass which is held by 3 springs in space, and the positive direction of x and y axis are shown here. These springs are rigidly held at these two points, and if we perturb this mass and let it vibrate, it will vibrate in that vertical plane or a 2-dimensional space, and the motion of that mass is defined completely by the motion x and y. Since it being a point mass, there is no angular displacement associated with mass m. Okay. It only translates along x and y direction. So, these are the 2 degrees of freedom. The 2 degree of freedom are x and y, independent degrees of freedom. Okay. Now, how do we analyze this problem? We will have to basically get the free body diagram, as we usually do, separate or isolate this mass and look at the free body diagram of this mass, and then arrive at the governing equation of motion, either using energy method like Lagrange's, or you can use Newtonian approach. So, before we do that, we just recall that if a spring is at certain inclination, and so the mass is located here, and it can move along y and x direction, but the springs are at some inclination. So, how do I define the forces, right? So, if this spring moves by a distance x in the horizontal direction, as we see here, and if this mass free body diagram is to be made, then I would like to know what forces act due to the horizontal displacement x. If I move this along the axis of the spring by x, or by let us say by let us say a z displacement, then of course this spring will offer us restoring force equal to k into z. But here there are multiple springs, and the motion is assumed x and y along horizontal and vertical direction. Now this is something which I think we discussed in the single degree of freedom system, that if we move this end of the spring by a distance x, this inclined spring having the stiffness k1 is going to be effectively stretched by a value equal to x cos theta, you can see that. And if x is the displacement along the positive x direction, okay, the one which we have assumed. So the net compression in the spring is going to be x cos theta. So the force which is generated in this spring, okay, so if I consider this as the mass, then the spring is going to create or generate a restoring force which is going to be Fs1x, okay, and this force is going to be proportional to the stiffness of the spring along its axis multiplied by the net stretch, which is going to be x cos theta, right. So Fs1x, which means the restoring force in the spring S1 due to a displacement x in the x direction, is going to be x cos theta into k1. So this is how the stiffness of the spring generates restoring force, but it should be understood that the spring being inclined to the x and y directions, so we have to account for that inclination, and that gets accounted for by using this cos theta term, right. If you really look at a typical spring mass system, we have discussed this, that if the spring is at certain inclination having its own stiffness k, then an equivalent spring mass system for the direction of motion along this k equivalent turns out to be k cos square theta or alpha, whatever angle that you consider. This is angle theta, and you can show that by taking a component of this S1x along this direction, okay. So the component of the restoring force along the direction x, this component of the force F is going to be Fs1x cos theta, which is basically going to mean that it is kx cos square theta, which actually means that the relationship between force and the displacement x is through k cos square theta, and that becomes the effective stiffness of the spring. Now this is some just the revision of what we have discussed right in the beginning of the course when we discuss single degree of freedom system. Now on similar lines, you can figure out what are the restoring forces coming from each of the inclined springs on the mass. So if I consider the free body, the mass m, which is shown here, the various forces which are going to be acting on this mass because of the stretching in the springs k1, k2, k3 along x and y direction are given by these forces. For example, let us say spring S3. So this S3 spring, if it is subjected to x displacement, it is going to get compressed, and that compressed spring is going to ensure that the mass is restored to its original position. So it is going to apply the force along this direction. So this is going to be the force due to the spring stiffness K3. The spring S3 is going to generate a force Fs3x, and that Fs3x restoring force is going to be equal to K3 cos theta 3 into x, okay. So if this displacement is x, then that K3 cos theta 3 x is going to be the force on on the mass m acting from the spring S3, which is having a stiffness K3 in the direction which is shown, because the spring getting compressed, the mass is going to get pushed back. But at the same time, the displacement, if it is along the y direction, positive y, then that mass is going to be causing stretch in the spring S3, or this K3 stiffness is of the spring S3. The spring is going to be stretched because in a slight change in the angle theta because of y. The amount of stretch that is going to generate is going to be again y cos theta 3. So the spring getting stretched because of the positive y direction, this is the net stretch in the spring. That net stretch in the spring is going to pull the mass towards its original equilibrium position, which is going to be somewhere along this line. Okay, so this spring which is S3 having the stiffness K3, if you move it in the positive y direction, then there is going to be net additional stretch in the spring, which is basically going to cause the spring to be in tension, and that is going to the tensed spring or stretched spring is going to pull it back, and therefore this force Fs3y is going to pull the mass back downwards, and therefore the force due to y motion, so Fs3y is actually representing the restoring force because of the y motion, is going to be again K3 cos I think it will be sin theta 3 y. Okay. Likewise, you can show the forces, restoring forces due to x and y motion to the mass generated through springs S1 and S2, and those are the forces which are shown here. You can cross check by giving positive x and positive y motion individually. You can show that these are the kind of forces which are generated on the mass. So having discussed and having shown these forces on the mass, and that basically represents the free body diagram for the mass m. Now you can write the governing equations of motion by applying the Newton's second law, which in a simple case is mx double dot equal to summation of all the forces in the x direction, in the direction of acceleration. So all of these forces are going to create their components along x direction, and those are to be summed up to apply this Newton's law to get the governing equations of motion. Now if you do that, we will not get into individual terms and all of these individual springs, but you can cross verify that this is the final equation of motion that you should get by applying Newton's law in x and y direction separately. And then if you substitute for f s1x, f s1y and so on, which we discussed in the previous slide, the equation finally in terms of the stiffnesses, individual stiffnesses K1, K2, K3 turns out to be this. Okay, so each spring is going to contribute, and then I can write this in a matrix form as we do for multi-degree of freedom system. The same, these two equations can be reformed into a matrix equation, and you can now notice that the stiffness matrix here is going to be having non-diagonal terms indicating a cross coupled stiffnesses or coupling between x and y, and which is going to be true because you try to move this mass in this direction, there is going to be unbalanced restoring forces acting along x direction as well because of this motion along y, and therefore any y motion is also going to generate x motion. When similarly vice versa, or any x motion will generate some y motion because of the peculiar configuration of this particular system. Okay, if we arrange these springs in such a way that the restoring forces are completely balanced, for example, if I symmetrically placed and the spring constants are identical and this angle is 0 degree, and then if I try to move this mass, there will be no y restoring force in the y direction. So then I can have x motion completely independently happening. But in general, this is how the stiffness matrix will look like, and you can then solve this governing equation of motion to get the eigenvalues and eigenvectors as we discussed. But that is not what we want to focus on. We want to now understand the modes and their character and the motion in the individual modes of this particular mass, right. So what we do, we take a small example. So using some numbers or numerical values to each of these parameters of the vibratory system and fixing a configuration, we can then be able to visualize the motion properly. So if you use these parameters of this vibratory system, you can easily show that the governing equations of motion would transform to this in terms of some numerical values of individual elements. And once you do that, you can solve it using whatever method that you feel convenient. You can also solve this by using a determinant, assuming some assumed solution here, and but basically the eigenvalues can be easily obtained since this being just a 2 degree of freedom system. But for a large degrees of freedom, you will have to resort to some numerical approach to get the eigenvalue analysis resulting in the natural frequency values. Now the first and second natural frequencies turn out to be 23.74 and 44 radians per second, and obviously you can use in fact any commercial software to generate eigenvalues and eigenvectors. The two eigenvectors corresponding eigenvectors are found to be this one and this one. Okay, so the first mode, this corresponds to the first mode eigen vector, which is the first mode shape given by these values, which actually means that if x displaces by 0.067 in x direction, if it is vibrating in only the first mode, that means when it is moving and executing vibration at its first fundamental natural frequency of 23.74, x and y will maintain their displacement relationship in this ratio. That means if x is equal to 0.067 units, y will be 0.31 unit. Okay. In fact, for convenience, it is quite usual and standard practice to convert these mode shapes into unit normalized form, in the sense that we set the first displacement unit or displacement parameter x to be unit value, and with respect to that, what is y. So typically if x displaces by 1 unit, y will execute I mean the y amplitude will be 4.625 when it vibrates at first natural frequency. On similar lines, when this mass executes vibratory motion at the second natural frequency, then the displacement pattern will be such that when x will have an amplitude or a unit displacement value, then y will at the same time will have a displacement value of minus 0.216. Okay, it does actually mean that if 1 and 0 minus 0.216 is the mode shape or a displacement pattern, 2 and minus 0.432 is also the corresponding mode shape. That means the mode shape is not an absolute displacement value, it is always a relative displacement of the degrees of freedom that you talk about. For example, if you look at this particular second mode, if x is moving 1 unit here, y is going to be moving minus 0.216 unit, which means that at one extreme the value of or the position of this mass will turn out to be here, and at the other extreme it will go to there, and this mass is going to be continuously shuttling back and forth in this fashion, so that at any instant of time the ratio of the x and y displacements are going to be maintaining this particular form. Okay, so that is the meaning of it actually. Now this is the unit normalized form for the spring mass system as has been configured in this case with numeric values which are obtained like this. Now what is going to be the general response of this mass when it is perturbed from its normal from its equilibrium position? What is important and we already know of is that if we perturb it initially by keeping the initial displacement x and initial displacement y at t is equal to 0 in this ratio, that means x is having a displacement of 1 unit and y a displacement of let us say this 4.6 units, right, something like this. And if you release it from this point, so at t is equal to 0, if we release the mass from this position as an initial displacement, the mass is going to oscillate and execute the fundamental mode of vibration, which actually is going to all the time maintain this relationship, and therefore it will execute a pure harmonic motion, because these mode shapes are obtained with that assumption that both the degrees of freedom are going to exhibit the motion in those degrees of freedom is going to exhibit a pure harmonic motion. Okay, their amplitudes may be different, but the frequency will be the same. Similarly, if I at t is equal to 0, if I displace this mass by in a way that x is 1 unit and y is minus 0.216 unit, that means somewhere here, and then release it at t is equal to 0, then it will oscillate and execute the vibratory motion in pure harmonic way with the frequency equal to 44 radians per second. Okay, and that is already known to us. That is how the mode shapes and principal mode of vibrations are. But the general motion when it is perturbed arbitrarily, the general motion is written in this form which we have discussed already, x and y, x as a function of time, y as a function of time, is given as a combination of the two normal modes omega 1 and omega 2 with their respective contributions and the mode shapes of individual modes at frequency omega 1 and omega 2 appearing in these two terms, right. There is another way to write this, and that also we discussed, that it can be written in this form where the mode shapes are unit normalized, and this particular value this is written as xr1 and xr2. Okay, so this is another alternate way to write that a and b are arbitrary constants. Now this is a general response expression. We need to find out the values of a and b and phi 1 and phi 2. This also is discussed in 2 degree of freedom system. But what we do is we assume x naught and y naught as the initial displacements given to the mass m in x and y direction at t is equal to 0, and assume that the velocities at t is equal to 0 is equal to 0. So this is an assumption that the initial velocities are 0, and we simply release it from certain specific xy position. Okay, so if you use these expressions for initial conditions, you can write this equation in this form, that at t is equal to 0, omega 1 t and omega 2 t will become 0, and then you are left with cos phi 1 and cos phi 2 terms with the mode shapes actually replaced by the actual numeric values. Okay, so this is how the equation looks like. If you take the time derivative with of this general response, this is the expression that you get, and then in that velocity expression x dot and y dot, if you substitute t is equal to 0, this is the initial velocity expression. Of course, you will have to set the x dot x naught dot and y naught dot as equal to 0, because these are the prescribed initial condition. When you do that, you can get the expressions for the unknown constants a and b, as well as phi 1 and phi 2. You can follow that process, and then simply, I mean, you just solve these two equations. It is possible to show that phi 1 and phi 2 both will turn out to be 0, and a and b will have expressions which are given by this. Okay, so if the expression for a in terms of x naught and xr1 xr2, now in this case I am using this value in the expression, but then if you treat this as xr1 as a general case and this as xr2 as a general expression, you can find that these are the actual expressions that you get. Okay, you can substitute for their individual numeric values to get the exact value of a and b, okay, based on the prescribed x naught and y naught. Okay, so the point is, we are trying to write this expression because we want to simulate and animate the motion of this mass as it vibrates either in mode 1 or in mode 2, or as a general combination of both the modes. Okay, so that is the reason why we are trying to arrive at a final expression. So finally, if you substitute for phi 1 equal to 0, phi 2 is equal to 0, and maybe you can keep a as they are, we will modify or substitute for adequate a and b values to animate or simulate the response by solving it. So obviously, if I substitute these a and b back into this equation, finally this was our general solution, and in that if you substitute phi 1 equal to 0, phi 2 equal to 0, omega and omega 2 are obtained already as the two natural frequencies, and of course the unit normalized mode shapes as given here. I can write this now that this is my final expression. If I get the values of a and b by using the prescribed x naught and y naught, I can, because this is already known to me through the eigenvalue analysis, because I know these mode shapes, the unit normalized mode shapes. How did I get this unit normalized? I divide this entire column by the first element, and then you can show that you get this one. Similarly here, you divide the first element by itself and the second element by the first element. That's the unit normalized mode shape. So now in this case, at any instant of time t, I can get the value of x and y. As the time progresses, I will get the value of x and y, provided I also know what is a and what is b. That I will know by the initial position, that is x naught and y naught. Now what I can have the initial position at t is equal to 0 somewhere here. So this value will become y naught and this value will become x naught. That is my initial position of this mass, which I will pull it and take it there and then release it. The three springs are going to pull it back and forth, and that's how the vibratory motion will ensue. Let's do this. So I am reproducing the previous expression here, and I know that if I want only mode 1 vibration, then the contribution from the second mode, which is this term, has to be 0, and therefore I set b equal to 0 appropriately. To ensure that I have only first mode vibration, that means the motion, vibratory motion is executed in pure mode 1 fashion, which means that the mass vibrates at its first or fundamental natural frequency, executing mode 1 vibration, no contribution from the second frequency. I will have to set the second term equal to 0, which can be done by setting b is equal to 0, and I can use an appropriate value of a. Now what I do is, if I set b is equal to 0, the initial displacement at t is equal to 0 will turn out to be this, cos 23.74 t becomes 0, equal to 1 for t is equal to 0, and therefore this is my initial displacement. Now I can use any value of a, because it will only be proportionate to the mode shape number 1. So I can use a equal to 1, 2 or 3 or whatever value. So what I do is I take some arbitrary a value, so that the initial position is given by this. Okay, so it does not matter, you can start this initial point at any position, provided you take appropriate value of a. By taking any number a, you will ensure that the x and y positions are in proper proportion. You can see that. So you can, if you divide this this value by this value, you can show that the mode shape still remains 1 and 4.625. That's the way it is. Now there is no reason why I have taken this value. You can choose any arbitrary value, but the animation has been done appropriately, so that's the reason why this number is taken. You can now see that at t is equal to 0, my x position is minus 0.134. so this is the initial x position at t is equal to 0, and y is minus 0.625. so this is my y position, so this is y naught. Okay, so I am starting from this as time t is equal to 0. That's my initial position of the mass, and now I will see as to how using this equation I can simulate the motion xt and yt, x as a function of time, y as a function of time. You may notice that since b is equal to 0, it is all going to execute based on this expression, which actually means that it has to vibrate at only one frequency. So the vibration is going to be harmonic with frequency of 23.74. Okay, this is how the animation would look like and go. So this is how the mass moves in the xy plane, and you can see on the left hand side this mass is going to execute vibratory motion about its mean equilibrium point. And what is interesting is, please look at this display, which is showing the motion along x axis. It started with negative x value, that's how it started here, and the amplitude is going to be as you see here. Okay, it's going to have this amplitude, and both the x and y direction motions are all properly shown here. Both of them are pure harmonic signals, and most important is that for a principal mode of or principal motion, both x motion and y motion is completed in the same period of time. That is how it can sustain harmonic motion and the same frequency motion. Okay, so both x and y is executing with the same frequency, and both of them are completing the same number of cycles in a given period of time. So this is how if it vibrates in mode 1, it vibrates harmonically and there is no contribution from other frequencies, a pure single frequency vibratory motion. That is possible because we give initial conditions that is conforming to the mode shape that has been obtained for that particular frequency. So the first mode shape is 4.625. So we ensure that at t is equal to 0, that ratio is maintained, and so if you see that this x and this y ratio is going to be 4.625, and that is why it has executed that motion. Let us now look at similarly what happens to the second mode. Now if we want the system to execute only pure mode vibration at its second natural frequency, then we know that the first term of this general solution, which is contribution from the first mode, should not contribute, which means A has to be 0 and B has to be non-zero. So we can give initial displacement here by giving x naught and y naught equal to b times this value, which is the case when t is equal to 0, cos 44t will become 1. So I can choose any arbitrary b value which I choose here, and the first the initial displacement now turns out to be, if you multiply it with minus 0.62, this equation will be this. Okay, I can as well use b equal to 1 and set this as the initial position, which means that I can use x equal to minus 1 and x equal to 1 and y equal to minus 0.216. Okay, but here you can see that the initial position here is y equal to 0.134 and x is minus 0.62. That is what is your initial position. Okay, you can actually see this one. This will turn out to be minus 0.62 if you measure it. 0.2, 0.4, 0.6 and some number value here, and 0.134 will be on the y-axis. They are not exactly the same scale, that's why you see a slightly distorted one, but it essentially means the same initial displacement as has been arrived here. So now this becomes your initial displacement at time t is equal to 0, and then if you release this mass by displacing it to be this value, which is conforming to the mode shape for the second mode, we expect the mass to execute harmonic vibration at its second natural frequency. So this is how we do it. You can start this animation and you can see that this mass is now executing a harmonic motion. You can see a pure sinusoidal waveform is being traced out in both x and y direction. This is how the motion is taking place. The time period will be corresponding to 44 radians per second. So essentially this capital T is 2 pi upon 44 radians per second. Okay, and you may notice that in the earlier case for the first mode, this same time period was 2 pi by 23.9 or so, which actually means the larger time period. Okay, so you can see that in the same time from 0 to 3, many more cycles have been completed because of the fact that the frequency here is more than the first mode natural frequency. You can see that if you just count the number of cycles up to this point, this 44 radians per second is roughly divided by 2 pi will be roughly about 7 hertz or 7 cycles per second. You can see 1, 2, 3, 4, 5, 6, 7 cycles are getting completed in 1 second. So it is matching with what number or numeric value of the second natural frequency that we have obtained. But more important again here is the way the vibration is happening, the vibration of the mass as we disturb it from the initial condition. The initial condition cannot be arbitrary, it has to conform to the particular mode shape. In this case, initial position was given at time t is equal to 0. Initial position was taken which has x and y values proportional to the mode shape. So it was proportional to xr2, which was I think 0, yeah, it was 0.216 negative. That means if x is positive, y is negative. This is exactly what is happening. If when it comes into this fourth quadrant, the x is positive, y is negative. When it goes into the second quadrant, x is negative but y is positive. That's why it is all the time maintaining the relationship of minus 0.216. Okay, and with that it executes pure harmonic vibratory motion at the frequency 44 radians per second. In the earlier case, the number of cycles were proportional to the frequency 23.74, and so that period was larger, and compared to here, you can also replay the earlier slide and show that the motion was slower compared to what you got in the second mode here. Okay, all right. Okay, now what we are going to now witness is that suppose we do not provide the initial conditions that neither conforms to the first mode relationship between x and y, nor conform to the relationship of x and y displacement at t is equal to 0 corresponding to the second mode. So, neither first mode nor second mode, an arbitrary motion. Okay. So, if that is the case, A is not going to be 0 and B is also not going to be 0, both A and B are not going to be 0. So, we take some arbitrary A and B values, and with that the initial displacement, if you use them, the initial displacement turns out to be this, which finally turns out to be this value minus 0.18 and minus 0.69. That basically is the initial displaced position of the mass at t is equal to 0. If we release it from here, please note that the ratio of this and this is neither this and nor this. It is definitely not this because both of them are negative signs. It is not this definitely because it is positive, and then the value, the ratio is also not going to be what is expected. So, when you give this kind of an arbitrary motion, you expect that this term is going to contribute at a frequency 44 radians per second, and this term will also contribute with a frequency 23.74 radians per second, right. And then the motion is not going to be a harmonic motion, which is a requirement for a principal mode or a principal motion. Okay. So, let us look at, if we give this initial condition, which actually means that this displacement, you can count and check that this displacement is minus 0.69 and this displacement is minus 0.18. They are not in the same proportion because of the x and y axis scaling factor, but the numbers are going to be exactly like these. Now, if we release it from here at t is equal to 0, let us look at what kind of a motion do you get. Look at this, it is not harmonic. Look at the time histories here. Are these harmonic motions? They are not. And look at the way x versus y displacement is looking like. Earlier, because both of them were harmonic, they complete one cycle in the same period of time, but this is not happening here. The mass, after you disturb it arbitrarily, executes this kind of a motion, and you can see this is the kind of motion that is being generated. Okay. This motion is not harmonic at all. It is periodic, but that period will be based on these numbers. So, the LCM of this 23.74 and 44. So, it will repeat after a reasonably long period of time, which is going to be some integer multiple of the fundamental period of the first mode and second mode. It will repeat after certain period of time, but it's definitely not a harmonic motion that you can observe in x and y both. So, this is a typical response that you get if we disturb this 2 degree of freedom with an arbitrary initial excitation or initial perturbation x naught y naught, which is not conforming to either the first mode nor with the second mode, and therefore both of the two modes contribute, and this this kind of a motion is observed, which is going to happen because the two frequencies are not commensurate. Let us look at the frequency spectrum of this response. That means basically it actually means that if I take the Fourier series decomposition of this signal, because there is only one harmonic signal, I will get one frequency. If I take a Fourier spectrum of this time domain data, I get a frequency spectrum or a frequency domain data, which has to show a single frequency, which is being represented here, which exactly matches as expected with the first or fundamental natural frequency of this particular spring mass system. Pure mode 1 vibration was observed, so only one frequency appears in the response, which anyway was seen from the time domain data itself. There is no need to get a frequency domain spectrum, but that may be required when we talk about a general response. Okay, so similarly for pure mode 2 vibration, the frequency with which this system vibrates was at the second natural mode, and which is almost same as the second natural frequency, and so basically you get again a harmonic vibratory motion, and a single frequency appears in the spectrum here. So this is how confirms that the two modes has single frequency response. But now if it is due to mixed mode, that means contribution from first and second mode, if I take a larger sample size so that they both execute one repetitive sample of data and then take the FFT or Fourier spectrum, the spectrum looks like this in the x direction and in the y direction. So this is corresponding to x vibratory motion, and this is corresponding to y vibratory motion. In both x and y, you get the presence of the first natural frequency and second natural frequency. As expected, these frequencies do contribute in the overall vibratory motion, and that is how it is being shown here. You can notice that this is almost harmonic with the first frequency, but there are these modulations, and I mean the low frequency is dominating, and that is how you see that this particular amplitude is stronger there, whereas in the first case there are two frequencies prominently seen, but second frequency also makes its presence in the y direction. All right, now finally coming to the orthogonality, orthogonality of principal modes, wherein we have shown that this UR transpose M US is equal to 0 for R is equal to is not equal to S, and is not equal to 0 for R equal to S. Now actually this motion which you have seen, which I can replay here as well, are showing the motion in this xy plane. So there is to a limited extent there is some geometric interpretation of this orthogonality. Now this motion of the mass in the xy plane takes place along this straight line, and it executes pure harmonic motion, both x and y cycles getting repeated exactly after the same period of time. In both cases you can see that this, if you consider this to be the vector, okay, or the plane in which it is vibrating, this vector in the second mode and in the first mode they are orthogonal, they are making 90 degrees, and when it is vibrating in this mode, the first mode, there is no other frequency that contributes, it is only pure mode 1 frequency, and in the second mode there is no other frequency but the second mode frequency, and it is possible to show geometrically they are at 90 degrees. The first mode motion and the second mode motion in the xy plane, they can be shown orthogonal to each other. You can see that, and you can verify that by the values that have been used for their individual modes. So you check the values of these mode shapes, okay, the values of these mode shapes, and put them as the initial conditions for both the modes. You can show that this line along which the first mode executes and the second line along which the second mode executes, they will be orthogonal to each other. There is a possibility that one can consider this to be a geometric representation of what actually is meant by the orthogonality of principal modes. If we change the parameters, that is these angles at which the springs were located, you can verify that this 90-degree modal vector orientation is valid irrespective of the configuration or mass. So it is a property of the system or for any system, and it's not by chance that we are observing it in this particular configuration. Okay. Now if additional degree of freedom, let's say z, appears, that if this mass is moving in a 3-dimensional space, then you will have another line about which it is going to vibrate, and then the three modes will be orthogonal to each others, and then in an n-dimensional space you can treat that to be 3 independent vectors, I mean 3 mutually perpendicular or n mutually perpendicular vectors in an n-dimensional space. Okay. So I have used 2 more other configurations of the spring orientations, and you can see that in each case, based on the values that you use of the same spring constants but orientations are different, you can show that the 2 modes are orthogonal to each other. Of course, if there are n degrees of freedom, then making a geometric visualization or interpretation may not be convenient, and it's not possible. So but in general we can say that all the modes that you get are orthogonal to each other, and to an extent the meaning of that is, if the system is executing normal mode vibration at a particular natural frequency or eigen frequency, then the displacement pattern of the other mode does not interfere or contribute to that motion. That motion is pure in that particular mode of vibration. That's precisely the meaning of that, and it's quite similar to the case of the principal stresses and the principal planes that you might have studied in the solid mechanics, where when the a stress element, when it is subjected to different stresses, applied stresses, there are planes along which only the normal stresses act, and those 2 planes are again orthogonal to each other. Okay, so there is no shear stress, only maximum normal stresses in the 2 orthogonally oriented planes. Those are the principal planes, on which only the normal stresses exist. So the summary of this lecture, we discussed an example which demonstrated the orthogonality of mode shapes or eigenvectors as we call them, the effect of initial conditions on the ensuing vibration response characteristic has also been explored, and demonstrated that they have a significant influence on the response that you get, the vibratory response that you get. The frequency composition is largely guided by the way you initially excite the system. These are the review questions based on this lecture. These are the answers.